as I said yesterday, the presentation of AstroGeoFit will be in 5 different lectures. So yesterday we saw the AstroGeoFit model, and today I'm going to talk about the estimation of parameters and certainty. In the plots you've seen yesterday, these are the gray areas. And I will first start with a reminder of what I talked about yesterday, which is the signal model. So we've seen yesterday the model has several components: the astronomical signal, the noise, and the time depth function. And since this is really the core of AstroGeoFit, I'm just going to go through it again with a slightly different spin. So hopefully all the equations will be very familiar to you at the end of the week. So the AstroGeoFit model has this form. We think that the data as a function of depth, which is a proxy, is the sum of an astronomical signal coming from the astronomical forcing, which is a function of time. But then we transform depth into time by a transfer function, so from depth to time. And we have some additional random noise that models basically everything that's not already in the astronomical signal. The astronomical signal, we've seen that this is a sum of periodic functions, where here we encode the amplitude and the phase. So if you're not convinced, this is how you go from this representation to the amplitude of each frequency and the phase of each frequency. So here, this astronomical signal, it depends both on the fundamental frequencies of the astronomical forcing, the amplitude and phase of these signals, and so it means that the response to the forcing is linear, and that we allow any kind of phase shift from the initial forcing to the response of the geological data. Now, second ingredient of the model, the time depth function. So this is parameterized by its derivative. Its derivative is, so to determine its derivative, we take a grid of depth, and then the parameters are the value of some points on this depth. And the derivative of T of D is obtained by first interpolating between these points and then integrating to get from the derivative to the time, which is our goal. The noise, it's an autoregressive process of order 2, which means that the value of the noise depends linearly on the value of the noise at the previous depth, plus some Gaussian noise, which has a given variance. And these two, phi 0, phi 1, phi 2, are the parameters of our model. And I insisted yesterday on the fact that saying this is basically defining a recipe to generate noise. So with this recipe, I can generate this noise, or an infinity of different realizations of the noise. It's like something that defines a machine where when you push the button, it generates a different realization of noise. And we've seen that to characterize this noise, we can use phi 0, phi 1, or phi 2. Or since the so-called innovation U is Gaussian, we can also define it completely by the autocorrelation of the process. So it is equivalent to give the yellow curve or to give these parameters. Or another way to say it is that this yellow curve is completely determined by these 3 parameters. So the full model in a parametric form with all the parameters, the time depth function parameters, frequencies, phase and amplitudes, and noise parameters. So in fact, here we have a recipe to generate fake data. And to insist on this fact, I denoted this quantity not by white data, so the actual data that we have at hand, the actual proxy, but some sort of theoretical model. And so what we have is in fact a probability distribution on how to generate, how to draw instances of something like this, knowing the model parameters. And so, in case it wasn't clear yesterday, this vertical bar, this pipe here, is the probabilistic notation for knowing. So these are fixed. This is what I know, and I want the probability of this fake data knowing the parameters. So, for instance, here I have fixed all these 4 parameters, and I generated several instances of realization. So, again, saying this is the same as saying this is a probability distribution. This is a recipe to generate fake data. And all of these are realization of these of this process. Now, if I replace this fake data, this way to generate stuff, by the actual data, so what is the probability of the actual data with this probability distribution, knowing the model parameters, this function thought as a function of those parameters, this is called the likelihood. And this is really the key ingredient of the model. This is what encompasses all the assumptions about the noise, about the astronomical forcing, and so on. So this is really super important. And so this is the mathematical notation, but the important thing is to think about the likelihood as the probability of the data knowing the model parameters. Another barbaric mathematical expression, I said yesterday that this is the parametric expression of the likelihood, of our likelihood. So here we have the difference between the data and the astronomical signal. This is thought as 2 column vectors. You have the vector of the column vectors of the column vector of the data, the column vector of the signal, and you do the difference. So you have 1 column vector here, but you use the matrix transposition. So now it's a row vector. Now you have the covariance matrix here, more precisely the inverse of the covariance matrix. So you have your row vector here, now the covariance matrix like this, and again the same column vector as here. So it's row times square matrix, it's still a row vector, times a column vector, this becomes a scalar. So this is basically the chi-squared. This is all that's in this exponential, well, I mean, except the -2. This is basically the distance between the model and the signal, weighted by the properties of the noise. And to finish off with the notations, this is the determinant of the covariance matrix. So that's the generic expression for a multivariate Gaussian distribution. Now, we said yesterday that one way to estimate those parameters is to, again, the likelihood is the probability of the data thought of as a function of the parameters. So if I maximize over the parameters this likelihood, I have an estimate of these parameters, which are called the maximum likelihood estimates. And finding the maximum likelihood estimate is the first step of estimating the parameters of the model. Now we move on to the second step. Once we have these estimates, so we estimate the uncertainty. So suppose I give you some geological data and I give you, and I say the amplitude of the astronomical signal is 2 in whatever units so suppose this is the eccentricity you're trying to reconstruct, and you say at this time the value of the eccentricity in the past was exactly 0.54. Or if you were talking about the Earth, it would be 0.005. You wouldn't believe me, you know? You wouldn't believe that the eccentricity 20 million years in the past, that with this geological data, you could say with certainty that it was 0.05. You have an uncertainty because the geological data is polluted by other things. Maybe there's kind of response, the response is not completely linear. And in general, when you estimate stuff from data, the data is not perfect. So you have some error bars, some uncertainty, and you want to see what are the parameters, what is the range of parameters which is still compatible with the data. Some parameters are going to be completely off. It's like there's no way these can fit the data, but some of them are compatible with the data. So the range of parameters where the likelihood stays kind of the same is basically the uncertainties we want to determine. Okay. Just a small reminder, in everything that I'm going to say today, the number of knots in the time depth function is fixed. So we just have the parameters of the astronomical forcing and of the time depth function and the noise, but the number of knots is fixed. And so we are going to do the retrieval in the Bayesian framework. And the Bayesian framework is in fact kind of simple. It's instead of computing the probability of the data knowing the model parameters, we want to compute the probability of the model parameters knowing the data, which makes, this is much closer to your practical situation, because in the practical situation, you don't know the model parameters, that's what you're looking for. But what you do know is the data. And so the formula relating the two is called the Bayes formula, and it goes like this. It says that the probability of the model parameters knowing the data is equal to your likelihood times the probability of the model parameters prior to seeing the data, and divided by something that we'll talk about later on. Again, going to say it twice because this is very important. This is the probability of the model parameters knowing the data. This is the likelihood that we've talked about at length since yesterday. And this is the probability distribution of the parameters prior to seeing the data. Let's take an example to understand what that means. And one thing that I always keep in mind when I do Bayesian analysis is communication theory by Claude Shannon. So suppose that an emitter is sending a message, a receiver is receiving it, but the communication channel is noisy. So what is the prior probability in that case? Suppose you know that the message is sent in English. So you don't know anything about the message, the particular message that is being sent to you, but you know that it is in English. So you know that words like I, am, and the are more probable than words that occur only once in a while, like centaur or just utter nonsense. It's like, it's more, if you read the text in English, I think you agree that it's much more likely to find the than XHGLI9GJE. So, and this is about, here we don't know anything about the message that has been, the precise message that has been sent to us. Now the message goes through a communication channel which is noisy. So here we are going to have the probability to receive A, but also B, C, and so on, when A is sent. So if the true message was A, we are going to have a certain probability that, in fact, we're going to receive C. And this is, so in this example, just like in the geological example, this is the term where you worry about the noise. And in the end, this is what you're trying to decode the message. So you want to know, knowing what you received, what is the most probable thing that was sent to you. So suppose you receive excellent with a Z, and you know that the communication channel makes an error approximately every 10 letters, and that the message is sent in English. So it's what's most probable is that the message that was sent is excellent, right? But you can think of this as nature sending us message. The real message is the astronomical forcing, so what was the position and the conditions of the Earth in the past. But we have a communication channel which is faulty, and which is basically the measurements, the geological measurements that we take. And now we are trying to find what nature sent us. In the context of the geological forcing, this is here the model parameters are all the model parameters we talked about so far. This is the likelihood we defined so far, and these are going to encode our uncertainties. So, in practice, in AstroGeoFit, you will see things like this. These are the posterior distribution of your parameters. So, for instance, here, this is the precession frequency. In blue, you have the prior, and in that case, you're very agnostic to what the precession frequency is. It means that here, basically, 49 is just as likely as 51, as 53, and 48. It's like arc second per year. This is what prior to seeing the data, you put very little information in what the precession frequency is. And after seeing the data, this is a probability distribution in the model parameters, and which is much more constrained. So the probability, okay, so we'll see it later. Now, in that case, this is the prior, and you see that it is much tighter. In that case, the parameters we were looking at is G3. This is a parameter which is well constrained, and from its current value, you can have an idea, pretty precise idea, of what it was in the past. Actually, you could do the same with the precession frequency, but here, this is just for illustration purposes. But in that case, it means that the posterior distribution is not allowed to go in there. Or it's almost as if it's not allowed to go in there. You will have your posterior estimate of G3 in these bounds, approximately. So far, we didn't talk about this part of the Bayesian formula. This is something we'll talk about tomorrow. But for our purposes, right now, the only thing you need the only way you need to think about this is a normalization factor, so that is a proper probability distribution. So if we want it to be a proper probability distribution on the model parameters, its integral has to be 1. Because the probability of all the alternatives has to be 1 in the end, the sum of the probability. It's like, for instance, you talk about the probability distribution of a dice. would it make sense to say that the probability to have 1 plus 2 plus the probability to have 2 and so on is 0.9? It doesn't make sense, because it's either 1 or 2 or 3 or 4 or 5 or 6. It doesn't make sense also to be more than 1. I couldn't even fathom what it would mean to have a sum of probability that is more than 1. It's just once you've defined all the alternatives, it has to be one of the alternatives with a certain probability. So this term in the posterior distribution here, so far, we are going just to think about it as something that makes it a proper probability distribution. So what is the interpretation in terms of this posterior distribution? So here, the probability to have k between 50.2 and 50.5, this is the area under the probability distribution. So the total area of this probability distribution is 1, as we've just seen. And the fraction of the area which is between those two bounds, this is what we call the credible interval, the probability of the credible interval, to have the precession frequency in these bounds. And so, yeah, the credible interval is basically the lower bound and upper bound, and it has a certain posterior probability defined by the area under the curve. And in that case, it's about 50%. One way to think about this, so sometimes people in the Bayesian communities, they say, well, the posterior probability is just a measure of belief. It's not like in the frequentist setting where you don't talk about posterior probability, and in the frequentist setting, the probability is interpreted as a frequency, and in the Bayesian framework, the probability is interpreted as a measure of belief. But you could also see this posterior probability as a frequency. So suppose you have 100 geological data sets. You estimate the precession frequency, and each time you estimate the precession frequency, you have a posterior distribution. And each time you find a 50% credible interval. So you have 100 data sets. For each of them, you have a 50% credible interval. So in this data set, it's going to be this. In this data set, it's going to be this. In this data set, it's going to be this, and so on. The true value of I mean, you will be right 50% of the time. The true value of the precession frequency will be included in your interval 50% of the time if you could know it. So this is a frequency, basically. And historical note, to talk about this kind of problem of interpretation of probabilities, in the communication theory, in the information theory, basically information theory is a frequentist interpretation of probabilities plus the base formula. So, I mean, there's no contradiction. The advantages of a Bayesian approach are that it's kind of simple, in fact. Once you've defined your likelihood, once you've defined your prior, then you have a way, consistent way, to incorporate some prior knowledge about the astronomical forcing in particular. You have a way to estimate all the parameters at the same time, so you don't run into the problems of having some parameters that don't talk to each other. Which is what we have today when we do the estimation of the time depth function with a fixed astronomical forcing. So when you use one solution, you don't propagate the uncertainty on that particular solution in the time depth function. Also, another advantage is that this methodology is well tested, and you have a lot of codes which are able to compute the posterior probability given those two elements. So I think one of the most, one of the best case we can make for Bayesian analysis is its simplicity. Okay, let's take a few examples of what the prior, likelihood, and posterior look like. So I'm going to take a generic parameter x, which is between -1 and 1. And suppose this is its prior distribution. And this is the likelihood, still as a function of x, illustrating again that the likelihood should be thought of as a function of the parameters. Now, this is the posterior. And the posterior is basically the product of this and this, normalized so that it's still a probability distribution. So in that case, you see that the prior is dominating. So the posterior probability is almost like the prior because the likelihood, the data is not super constraining, in fact. So you have a wide uncertainty due to the data, and you're much more constrained by the prior. What you want is the other case. It's when the prior is pretty broad. Prior to seeing the data, you don't have really any idea about the value of the parameter. Now you have some constraining data that it's putting strong constraints on the parameters, and the posterior is dominated by the data. So this is why in AstroGeoFit we always plot the prior and the posterior, because here you can see that the likelihood is not that constraining. The posterior is almost the same as the prior. So in fact, in that case, the likelihood is providing us only limited knowledge compared to the prior. Is that clear? Yeah. Okay. Now we can have probability distributions in 2 dimensions. So here I denote the 2 parameters of my probability distribution, x and theta. So x could be an astronomical frequency, and theta one of the parameters of your time depth function. So you can represent your prior distribution and likelihood as a heat map. So here the probability, in that case the prior is uniform. The probability to be in there is constant. So you don't have a higher probability to be there than there, but you have a 0 probability to be outside. It's like your parameters are in that box, for sure. Where in that box you have no idea, but they are in that box for sure. And suppose the likelihood falls in that box, then the posterior is just proportional to the likelihood. So here the only constraints, in that particular case, the only constraint comes from the data, from the likelihood. In that case, you see that the prior is at the center, the likelihood is there, and because the prior is at the center, the posterior is just slightly more towards the origin than, it's like the prior is pulling back the estimate from the likelihood towards its preferred values. One of the things you don't want is, suppose this is your prior, so the probability to be in those bounds is, so you don't know where you are, but you know that you are in those bounds, and you have a probability 0 to be outside these bounds. Now the likelihood is like this, and when you compute the product of the two, you see that the posterior is chopped. So it means that the likelihood is contradicting very strongly your prior. So in that case, you don't just say, okay, this is my posterior, I'm going to publish my paper. You say, well, there's a problem here. My prior is contradicting my likelihood. So again, think of the prior saying there is a 0 probability to be in there. It's like you are as sure as anybody has been sure about anything in the universe that the probability of being there is 0. But the data is saying that it is not 0. So, you don't just publish this, you just think about your prior. Maybe my prior wasn't so good. Do I have good reasons to believe that my probability is non-zero here? Or maybe my model is faulty and is retrieving values which are unrealistic. which are absurd. Same situation in 2 dimensions. You are sure that you are in that box. This is the likelihood, which is outside this box. So in the end, the posterior is chopped. Just zoom on the posterior, you see that the constraint imposed by the prior. Another situation you need to be aware of is this one. You have your prior here, your likelihood here, and the posterior is in between. That's when you do the product of 2 Gaussians, which are symmetrical with respect to one value, the product is a Gaussian-like, is a Gaussian centered at the mean of the 2. Here you have the prior here, the likelihood here, and the posterior is here. But just like in the previous case, this means that your likelihood is contradicting your prior. So again, what you don't want is to publish this posterior without any discussion. And this is super important. I've seen in several articles people doing this mistake. Oh, I have this estimate, this estimate. They are incompatible, but I'm going to take the mean and say, well, this is the true value of my process. You know? So it's like, suppose you have an estimate of the precession frequency at 60 arcseconds per year plus minus 1, and 40 plus minus 1, and you say, well, it's 50, and it's compatible with what I know, so everything's good. No. There's either a problem with your prior or likelihood, possibly both. Another remark. So you see that the tightest constraint wins. So this was my previous example with the prior here and the likelihood here, and they have the same width. Now if I make my likelihood tighter, more concentrated around one point, you see that the estimate that was in the middle shifts towards the value that is the tightest. So the tightest constraint wins. Okay, so this is not the right title of the slide, but anyway. So here, what I did to evaluate the posterior is I took a grid of values of x, I took a grid of values of theta, and for each of these values, I compute the product of these, and then I normalize by the sum of the integral of this function. So suppose you have, in your grid, you have 100 values. So in that case, I have 2 parameters, 100 times 100, it's 10,000. Evaluating the posterior on 10,000 values, it's completely doable. But in AstroGeoFit, we typically have 20, 30, possibly close to 100 parameters. So suppose you have 30 parameters, and you just have a grid of 100 parameters, 100 values per parameters. So yes. So what the software in MCMC does to evaluate those posterior distributions might seem counterintuitive, but it's in fact to generate samples from this distribution. So you generate fake samples from this distribution, and if you have enough samples, their empirical distribution converges towards the true distribution, the theoretical distribution. So, to explain how MCMC works, we're going to use an image. So suppose this is your likelihood valley, and the height of the mountain is just is proportional to the posterior, which is proportional to the likelihood times the prior, as we've just seen. So now you have a frog jumping in that mountain, and the coordinates of the frog represent the position in the parameter space. So where it is on the Earth's surface, latitude and longitude, these are the parameters of the model. And where it is height-wise is the height of the posterior. So the frog is very careful. So it's like there's a proposal, like I might jump, the frog might jump there and considers it. So if the proposal, so this proposal is generated randomly. So the frog asks a computer, and the computer is suggesting randomly one point where the frog is. Now, whether this proposal is going to be accepted is determined by so the exact formula is a bit more complicated, but I'm going to take a particular case, which is the ratio of the probability of the proposal time divided by the probability of where the frog is. And you take the minimum of 1 and this. What does it mean? It means that if the proposal is higher, the frog jumps with probability 1. If the proposal, if you find a better, if you find something which is higher which is closer to a summit, at least higher, you jump with probability 1. Now, if you jump to a lower area, to a lower position, you see that the probability to jump there is not 0. It's the ratio of the two probabilities. So if you go from something very high to something very low, and this ratio is very close to 0, it's very, very improbable to go there. But if you're there and you go just a little bit below, then the probability to go there is still 0.3, 0.2, so it's like it doesn't never happen. And this particular feature is very important, because if you didn't allow to go lower, you could never do this path. So getting from there to another region of high probability. So it's a little bit like in quantum physics with the tunnel effect. It's like you have a well of potential, but you still want to go through that well of potential. And so here you need a fairly improbable sequence of events, because you need to go down again, then you need to find a path toward there, maybe you're going down again here, and then you're going up again, and you find another peak of maximum likelihood. So if we didn't have this possibility to go in a valley, we would be stuck at the local maximum, whatever that is. So in an MCMC algorithm, you need to select several things. You need to select the starting point, then the typical width of the jumps, and the number of jumps. So this and all of these pertain to the convergence of the algorithm. And this is what I'm going to try to illustrate. So yeah, maybe something I can mention is, well, no, we'll see this. So for example, this is one particular choice. The jumps are this big, but I could have this starting point with jumps which are much smaller, and a different number of iterations altogether. Okay, so let's see an MCMC in action. So here I have my proposal distribution. Here I don't accept it, I don't accept it. Here I accept it, I go there. Now I accept it, I go there. And on the bottom, I'm plotting a histogram of the past values of the parameters, of where the frog was. This is so in each box, this is the box, the value of the box in heat map is proportional to the number of times I went there. So now we go 10 iterations by 10 iterations, and we see that the histogram is starting to be populated. Now 100 iterations per 100 iterations. And you see that where the frog was is kind of similar to our target distribution. And now we see with tens of thousands of iterations, the empirical distribution looks a lot like the target distribution. So in that case, the only thing the frog knows are the value of the posterior and the prior at the proposal distribution and where it is in the chain. Let's see now what happens if you so in that case, you make jumps which are far too big. So you were in a pretty high probability distribution. In a region with a high probability distribution, and you want to go too far. So you had a good starting point, but you're just trying to go down, and it's never accepted. And you see that the acceptance rate is here, so it's the fraction of proposals which are accepted. Here it's very small. In the previous example, it was about 30%. Now it's just a few percent. So it's not zero, because once the frog started to see a region of the parameter space which is a little bit less probable, it could start walking around and not being on the peak and just not going anywhere. But you see that the convergence is not as good. It's like we're almost at the end of the iterations, and it doesn't look as good as before. No. Okay. So this is another example where the starting point is here, and it's far from the region of high likelihood. So you see that in that case, the frog is okay when it goes toward the region of high likelihood. So here the proposals are not so good, but it's moving towards the region of high likelihood. Yes, so the question is, how is it going to work out in the end? And it seems like, okay, now we found the peak of likelihood, and the walker, or the frog, stays there. So now we now have an acceptance rate which is pretty good. And in the end, we're going to converge to the right distribution. So this is the histogram of the past value of the chain, again. But in that case, things ended well, but it might not always be the case. So sometimes the starting point is so far from the region of high likelihood, you can have billions of iterations, it's never going to find the region of high likelihood. And so this is the occasion to introduce an important notion in MCMC, which is the so-called burn-in phase. So when you do your MCMC chain, it's typical to discard the first third or even the first half or first 20%, because it's when the chain was trying to find the region of high likelihood. So now it found the region of high likelihood, it stays there, and you keep the samples in that region, but you discard the burn-in phase. Another important notion in MCMC is called thinning. Because of how MCMC works by choosing jumping from gray point to gray point in a sequential manner, the probability to this being there is correlated with having been there. Being there is correlated with having been there. But if you want to estimate a probability distribution, it's always good to have statistically independent samples of this probability distribution and not correlated samples. So what you typically do in MCMCs is to take one sample every 100 samples, or one sample every 10 samples. Because if you don't do this, you might have apparent correlation between the parameters, but which are not true correlations. They are correlations due to the fact that you explore the space little by little, step by step. So how does it work with the genetic algorithm? In fact, the genetic algorithm is itself a random generation of species, and if you run it different times, you will find different peaks. So we run several times the genetic algorithm with slightly different assumptions randomly. And the genetic algorithm is going to be good at finding locations which are near the peaks of the likelihood landscape. And then the thing is, from each of these starting points, we can start an MCMC chain. So you will have an MCMC chain exploring this peak, this peak, this peak, this peak, this peak. And what Eugene is going to talk about today probably is stacking. You're going to mention stacking, right? Yes, okay. And when we do stacking, what it means is that we just combine the chains of all these different peaks. And we don't, so there's a little technological innovation in the AstroGeoFit paper, which is a way to combine these different chains by accounting for the fact that some peaks are higher than others. So it's possible that the chain is stuck locally in a peak which is very low compared to another one. So you don't want the samples of this chain to have the same weight as the samples in this chain, because it's still more likely to be in there than in there. So there is a way to, like combinations like this exist in the statistical literature, but we found a way to combine them in the context of AstroGeoFit. Okay. So, for example, these are, if you run the genetic algorithm, you're going to have a lot of different models at the beginning. Then it's converging progressively towards a certain solution. From each of these solutions, so if you do the uncertainty with MCMC, just starting from the very best solution of the genetic algorithm, you're going to have these uncertainties, and you see that the uncertainties are incompatible in some places. You know, like they are too tight. The uncertainty, the value that we retrieve is incompatible with the true value. But if we run the genetic algorithm several times, we start the MCMC chains from the maxima that were found by the different instances of the genetic algorithm, and we combine them, then the error bars are much more realistic. So the true inverse sedimentation rate is included in our error bars. Now, so yeah, quick point. Now, how do you propagate the uncertainties on the parameters of the inverse time depth function to the actual time depth? And there's something which is very simple with MCMC. It's like you have a chain of theta n's. For each value of the past, for each value in the chain of theta of your parameter, you can do this integration. You know, like once this is fixed, this is a function, a deterministic function, this is a deterministic function. So you can have an estimate of the depth, the time at a given depth. Now you take another value of your chain, you do again this calculation. So each time you have a value in the chain here, you have an estimate of your time at a given depth. And now if you plot the distribution of this time as a function of depth, then you're going to have an error bar. Finally, you can use you can use your recovered signal to do some absolute age time estimation. So suppose you have an astronomical solution, so generated with a computer program with a numerical integration of the solar system in the past. And you take your reconstructed signal here, and you compute the correlation of this reconstructed signal with the astronomical solution. So here the astronomical solution is in red. This is the classical way. This is the eccentricity from the Laskar 2010 paper. And if your reconstructed eccentricity signal and your reconstructed eccentricity signal is going to match more or less well with the astronomical solution as you slide it across the astronomical solution. And at some point, you can find a minimum of chi-squared or a maximum correlation, and you say, so actually this happened at this particular time, and you can use the uncertainties that you computed on your model parameters to estimate an uncertainty also on this absolute time determination. Okay, so to summarize, the important thing, the takeaway message, is that you compute the posterior probability which encodes the uncertainty on your parameters. This is the formula you use to compute it. So we have already determined what the likelihood is. The prior of the parameters, they are important insofar as if you have unconstrained prior, then you rely completely on your data to bring you some constraint on the parameter, or you can have a prior where you impose your model to have a certain parameter, which has the advantage of reducing degeneracies between parameters. So it might be a way to improve the precision of your estimates, but you need to have good reasons to put your prior there. You can't just say, oh, actually, I want to increase a little bit my precision on the parameters. I'm going to reduce the degeneracy between parameters, so I'm just going to put tighter priors. And actually, this is a great way to end this lecture. You never, ever put information from the data in the prior. It's like if you start saying, oh, actually, I've seen the data once, I'm going to change the prior, then you converge to what your initial idea was. And you're going to converge with smaller and smaller error bars, so you're going to be more and more sure about something that is probably completely false. So this has to be determined prior to seeing the data, and you don't update it. Or in very specific cases where you know exactly what you're doing. Thank you for your attention.
All right. So typically for a given age in million years, right, we have a table to report to for having a number of values of G's and values of S. So how would we define the range of which are these priors, right? So how would we define the range of these priors?
So one consistent way to do it would be if you have, for some reason, an idea about where back in time your data set was, you would propagate the motion of the Earth with some uncertainty on top of it, corresponding to the uncertainty you have on the current values. Then you propagate from these different starting conditions what the value of the frequencies were in the past. And the range of these frequencies the distribution of these frequencies is used as a prior. So this encodes the idea that your prior is coming from the current values, which are determined very precisely, plus the fact that you have some uncertainty that grows in the past.
Yes, to add something to that, for example, the curve here, the PDF that is plotted here, I don't know if it's this one, but it might be, correspond to, if we start from the present condition, when you go back in time, of course, the motion is chaotic, so you cannot say precisely what would be a G at 200 million years. But what we can determine in a precise way is the evolution of the PDF. You do it in a statistical way, and this is some work we have done since a long time, and more recently with in the paper with my student Wang. And so you have like that a PDF, which is what the chaotic evolution propagates with the uncertainty back in time. So it's something that will spread more and more with time. But you can also be a little bit more conservative. You can also say, oh, I take, for example, I'm looking for something that is at 70 million years, but I don't take the PDF at 70 million years, I take the PDF at 100 million years. So it is a little bit more spread, or at 200 million years. You see? That gives you a little bit more margin. So that's for the G and for the S. For the precession is really, so the G and S are not evolving much in time. They are just evolving in a very little way due to chaotic diffusion. The precession frequency, on the opposite, is evolving in a large amount, as I show in my first day presentation, because of the tidal evolution of the Earth-Moon system, tidal dissipation. So for this, if you want to make a prior, of course you can, if your signal of precession is very present, you can make a very wide prior, but you can also use the model we have for the Earth-Moon evolution and take it as a reference, but you need to put some, for example, in the paper of Mohammad Farhat, as was mentioned by Eugene yesterday, the uncertainty is not the true uncertainty. It's the uncertainty of the model, of the parameter, when you evolve the system. So you need to put, you take this value, but you put a wider uncertainty around. That's the way to, does it answer your question?
Absolutely.
Right. So if your prior and your data constraint share no probability space at all, so you've made a mistake either with your prior or your data is just noise or something, how does AstroGeoFit work? Does it stop? When do you know that? Do you have to wait until your figures come out and you've kind of mixed your prior and your likelihood completely, and it's within neither of their possibility spaces?
You would diagnose it in the end.
Okay, so the program will still run and it will give you an unrealistic posterior distribution.
Yes.
And maybe something need to be mentioned also is that sometimes you put a prior and you find that your posterior distribution is exactly the same as your prior.
Yes.
And in this case, it means that your data didn't bring any information.
Yes.
So the good signal, for example, here, you see the distribution of the posterior distribution is different from the prior. So here you know that you had some constraint given by the data. So you are quite confident that this is a real observation. But specific also for the G and S, very often you see a posterior that is very similar to the prior, which means you didn't get any real information from the data.
Arsene, are there convergence diagnostics in like MCMC convergence diagnostics?
I don't think so.
Okay. So maybe this is something that we will include in later versions. So you see that here, suppose that I stop. So this is my target distribution. This is what I'm trying to draw from. You see that if you stop. So here I generated 100,000 steps, MCMC steps. But suppose I decide to stop the computation at a number of iterations which is smaller. So if I stop at 30 iterations, you see that I have a very, very bad estimate of my target distribution. 100, it's still very bad. So you see that you don't want to stop too early. And it's good practice. So ideally, we would have some convergence diagnostics which tell you there is a good chance that your algorithm has converged. But in the absence of it, in the current version of AstroGeoFit, I think it's good to increase progressively the number of, to run several times the MCMC, and to see that from a certain number of iterations, the posterior doesn't change anymore, the posterior estimate.